Hello, my name's Roger Watson and welcome to this session on common statistical concepts. First of all, let's revise the characteristics of levels of measurement which were looked at in more detail in a previous session. Levels of measurement can be classified by their ability to classify, to order, whether or not they have equal units and an absolute zero. So the nominal level of measurement only classifies things. It doesn't order them, it doesn't have equal units, and it has no absolute zero. The ordinal level of measurement classifies and orders things, does not have equal units and no absolute zero. The interval level of measurement classifies, orders and has equal units but no absolute zero. And the ratio level measurement has all of these properties. When we're looking at statistics, we need to decide which level of measurement we're using. Ordinarily, interval and ratio levels of measurement can be treated much the same and treated as if they are normally distributed. Ordinal measurements can't be. Ordinal level measurements are analysed using non-parametric statistics, which are actually quite complex, and we're not going to cover them here. So we're going to work on numbers which we assume are normally distributed. I will explain later in this session what a normal distribution is. Why do we use statistics, and what does the use of statistics add to your interpretation of data? Well, it can tell you if the result you've observed happened by chance. Why can't you just claim that your treatment worked? It can tell you how likely it is that you will get that result again. And can you compare your result with that of someone else doing the same trial or another trial carried out by you? And how do you know how many people you need in a trial or a survey, and why would you need to know this? These are all the sorts of questions that can be answered using statistics. We're not going to answer all of these or look at all of these in this session, but we will look at some of them. First, we're going to look at describing data. So, take the following results from 100 nurses in a statistics examination. Those are the raw data from the 100 nurses. What can we do with these data? Can you describe the results of the examination? Can you summarise them? What was the average mark? What was the spread of the scores? And what were the highest and lowest marks? So what's the first thing that you would do if you wanted to do this? Well, the first thing that I would do is order the data from smallest to largest, like that. There at least you get some idea of what the data look like, but only a very crude impression. What can we do next? So what is the average mark? Well, one way to find the average mark is to look somewhere in the middle of the data, if they're arranged like this, and to highlight the most commonly occurring number, which in this case is 56. And this in fact is called the mode. The most frequently occurring number is the mode, and in this case it's 56. The next thing we can do is to find the midpoint in the data and highlight the number that's at the midpoint or the numbers around that midpoint. This is called the median. Please note that if one of those numbers had been 56 and the other one had been 55, the median would be the average of those two numbers, 55.5. So what is the mean score? Well, you can't actually see the mean score in the data. but we know that it's around the centre somewhere. But how do we calculate the mean? Don't be put off by these equations. The mean is calculated like this. The mean, which is represented by the Greek letter mu, is the sum of all the numbers that you have available divided by the number of those numbers, and that letter epsilon, the squiggly letter, that means the sum of. If we do that calculation, then we get a figure of 52.62, and that's the mean mark. That's another way of describing the average. So the mean, the mode and the median are all described as the average, but they're all different. So how does the mean compare with the other measures of what is called central tendency? Well, the mode is a perfectly useful number. In this case it was 56, but please note that sets of data can have more than one mode. If there are two numbers there in equal numbers, for example, you could have 52 and 53 as modes if they were both there in equal numbers, or the mode could be 52 and 57, just depending on which numbers were there in equal numbers. That would be called bimodal. So it slightly lacks utility from that point of view. The median, which is the midpoint in the data, is also very useful under some circumstances, but is not sensitive to skewed results. It doesn't tell you anything about the numbers above or below that. The mean, which in this case was 52.62, is very useful because it takes all of the scores into account. But of course, as you can probably work out, it's very sensitive to extreme values. None of these particular measures of the average is perfect. They all have their own advantages and disadvantages, but the mean is the most commonly used because it has other uses and it's most useful in statistical analysis. How do central tendency and levels of measurement compare? Well, it's valid to use the mode if we're working with nominal level data. The mode or the median can be used with ordinal level data, and all three can be used for interval or ratio level data. And that's what I meant at the beginning when I said that interval or ratio level data can be treated almost identically in statistical tests. How do we describe the spread or the variation of data? Well, we can look at minimum and maximum scores, or the interquartile range, or the standard deviation, and I'm going to look at each of these in turn. If you order the data like I've done here, the minimum and maximum scores are very easy to spot. And from that we can work out a range, which is the minimum minus the maximum, which in this case happens to be 90. If we take the median of the two halves of the data, this is what's called the interquartile range. And in this case the interquartile range is 48.5 to 59.5 because we take the average of the two sets of numbers. Next we can work out a value called deviation. The deviation is simply the sum of the differences of all the numbers from the mean divided by the number of numbers. The problem with deviation is it can have negative values. It doesn't in this case. It's equal to 9.15, but where it does have negative values, that makes it very difficult to use in calculations. To get rid of the negative values, we can square the values in brackets to derive the variance, which in this case is 176.52, but please note that that's not expressed in the original units. You may say, what use is variance? Well, variance is useful, for example, in working out the correlation between a drug dose and a measure of pain. You can't compare the two units directly because they're different measures, but if you work out the variance in those measures, that can be put into a statistical test called a correlation test. However, it's plain here that the value of variance lies outside the range of values in the data set, which range from 0 to 90. If we take the square root of the value above the denominator, then we can divide that by n and we derive a value called the standard deviation of those data, and that is expressed in the original units, and the standard deviation of the data is 13.29. Next I want to show you what use it is calculating the standard deviation. In other words, why would you do this? And to understand that, we use the 68, 95, 99 rule. In other words, we know where data are normally distributed that 68% of observations fall within one standard deviation of the mean. So if we know the mean value and the standard deviation, we immediately describe the data. We don't usually use two standard deviations, but that describes 95% of the data, and three standard deviations describe 99% of the data. This is expressed in the standard normal curve. And this is a standard normal distribution showing the Z scores there. The Z scores are standardized scores from any set of data which are equivalent to the standard deviations. So 1 on either side of the mean is equivalent to 1 standard deviation, 2 and 3, and so on. Please note that in theory you can never fully describe a set of data. That line on the graph never actually touches the x-axis in theory, although it gets very close to it. So let's go back to a more practical example using the exam scores. Here the mean is 52.62, the standard deviation is 13.29. So 68% of the observations fall within one standard deviation of the mean, in other words from 39.33 to 65.91. And there's the value for 95%. They fall between 26.04 and 79.2. They clearly describe a larger amount of the data, and likewise for 99% of observations. For three standard deviations, that falls between 12.75 and 92.49. We'll come back to the use of the standard deviation beyond this. Next, let's look at sampling and populations. So let's look at the relationship between a sample and a population and how these statistics can help us to understand that. If that's the population, then a sample is simply a subset of that population. It's very rare to use the whole population or to have the whole population available to you. For example, if we wanted to find out something about all the students in our university, we wouldn't have access to all of them. There would be far too many. What we could do is take a sample. What we then want to know is how accurate is that sample. One way of doing that would be to take repeated samples and then to compare them. However, we don't have to do that, and I'll show you why. So next, let's turn to something called the standard error and how that relates to sampling distributions. When we repeatedly take samples, we don't get the same mean value every time. We get a distribution of those means, and it looks like this. And you can see that the larger the sample, the narrower the range of those means. So for each of those sample sizes there's a distribution, but it's slightly different. And the standard deviation of any of those distributions of the means is known as the standard error. And the standard error is the standard deviation, represented here as small sigma, divided by the square root of n, the number of people in your sample. So for example, for the exam results, the mean was 13.29. Divide that by 10, which is the square root of 100, and we get 1.329 as our standard error. So you can see that from the mean you can calculate the standard deviation, and from the standard deviation you can calculate the standard error. But you are probably wondering, what use is any of this? And I'm going to explain that this is useful in telling us something about how accurate our measurement of the mean is. And this is described next in the use of confidence intervals. A confidence interval is the mean plus or minus a z value multiplied by the standard error. Now, you don't need to know much about z values. Z values, you saw them on the normal distribution curve, are the values along the x-axis, which are standardized measures which apply to any measure, height, weight, or whatever. We can convert them into those z values. To describe 95% of those data, the actual value of z is 1.96, and that's commonly used because we most commonly work out 95% confidence intervals. So you don't actually have to think about what z is, the value is 1.96. So for a real example from the exam results, the 95% confidence interval is the mean, which is 52.62 plus or minus 1.96 times 1.329, which is the standard error, which gives us a 95% confidence interval from 50.02 to 55.22. Please note that what the confidence interval tells us is, it tells us that in 95% of the cases where we take a sample from that population, our mean will fall within those values. Next, one or two-tailed statistical tests. This is a concept that you will come across, although one-tailed tests are actually rarely used these days. You use a one-tailed test if you have some expectation about the direction of any difference. For example, if you tested young people versus older people, for example, adolescents versus children, you'd expect the adolescents to be stronger or faster or to do better in examinations or whatever. You'd use a one-tailed test. But we rarely have the luxury of knowing that, and it's now considered more proper in every case to use two-tailed tests. And in fact, the statistical package for the social sciences, SPSS, uses two-tailed tests as a default. Another related concept is type 1 and type 2 error. Essentially, type 1 error is rejecting the null hypothesis when it should have been accepted, and type 2 error is accepting the null hypothesis when it should have been rejected. So type 1 error, there was no difference between your two groups, but you claim there was, and you protect against type 1 error by setting sufficiently low values of probability. This is why p is conventionally set no larger than 0.05 and often below that. In type 2 error there was a difference, but you missed it, and this occurs when you don't have sufficiently large sample sizes. To avoid type 2 error we use something called power analysis, which will be the subject of another session. And finally, and very briefly, choosing a statistical test. The first thing you have to do when you're choosing a statistical test is to decide which kind of data you have, interval or ratio level data. If they are, then you can test whether the data are normal or not, as that will also dictate which kinds of tests you use. If it's normal, or if it's non-normal. Let's move on and look at what happens when it's normal. If the data are normally distributed and there is only one group and the variance is known or unknown, this makes a difference to the test you're going to use. If the variance is known, you can use a one sample z-test. If it's unknown, you can use a one sample t-test. If there's more than one group, let's move on and look at that. So your data are normal, but you've got more than one group, and you want to compare two groups. You can have data that are either non-paired or paired. Paired data are where the same group is measured twice. Non-paired data refer to different groups, for example, men and women. In the case of non-paired data, you can use an f-test of variance to examine that data. We'll come on to that later. For paired data, you can use a paired samples t-test. So let's move on to look at the f-test of variance and what that tells us. So your data are normally distributed, you've got more than one group, and you've applied an f-test to see what type of data you have. And you want to compare the two groups of data. These can be either non-significantly different in terms of variance or significantly different. If they're non-significant, then you can use a two-sample independent t-test for equal variances. If they're significantly different, say two-sample independent t-test for unequal variances. If we want to compare more than two groups, let's look at that next. If the data are normal and you're comparing more than two groups, you need to decide whether this is one level with more than one group or more than one level with more than one variable. For one level with more than one group, you can use a one-way ANOVA test. For more than one variable, you can use a two-way ANOVA. ANOVA stands for analysis of variance. If you want to look at the association between two groups, you would use a Pearson's correlation. Next, let's look at data that are non-normal and the tests that can be applied to these data. If the data are non-normal, we can be considering all of the situations we would be for normal data. For example, we can be looking at one group, or comparing two groups, or comparing more than two groups, or looking at the association between two groups. For all of these, there are equivalent non-parametric tests. For one group, we would use the Wilcoxon one-sample median test. To compare two groups, we'd use a Mann-Whitney U-test. And for more than two groups, we would use a Kruskal-Wallis H-test. And to look at the association between two groups, Spearman's ranked correlation. Thank you very much for listening. That's my email address if you have any comments or questions, and you can follow me on Twitter. Once again, thank you very much.